Welcome to part 2 of the physics slides on particle physics by Peter Horter. Please pause the video and make sure you've got these things available, particularly for today, an A-level formula sheet and pen and paper to make some notes on the standard model. So this is a selection of what we're going to be looking at from the syllabus. So I've cut and pasted various parts. And as I'm going to talk about the syllabus, it's difficult to decide in what order to teach it. There's a large amount of knowledge required for the final exam, and it's possible to approach that knowledge in a number of ways. Now, many of the textbooks start with a chronological approach, and that makes some sense in terms of showing the knowledge as it built up over time from the early 1900s onwards. The downside is it's hard to get a picture of where you're heading. So I'm going to take a different approach from most of the textbooks. And I'm going to start with what we now know and then work in some senses backwards so that you can build up the knowledge with a structure in which to hold that knowledge. As you can see here, there are lots of unusual words: antibaryons, pions, antiquarks. We need to be able to define all these terms quite carefully by the end, and so having a structure makes learning them much easier. The language is difficult and you will need to practice it, and for many of you some sort of flashcard might be the answer, or a mind map, something to allow you to keep on top of the language. We're going to deal with quantities like charge, which you've come across every day. So hopefully at primary school or in the lower school, you've seen tricks like rubbing a rod to charge it and then making a stream of water bend. We can see the effects of charge in everyday life. Whereas the effect of baryonness, that property of being a baryon and how baryonness you are, a bit or a lot, which is often referred to as the baryon number because it's quantized. It can only take values of 1, 2, and so on. They're quite abstract. We can't see their effects, but they are nevertheless properties in the same sense. So the more you can believe that, the more you can get a feel for that with these abstract properties, the better. So where we're heading is what physicists call the standard model, sometimes called the most tested theory in all of human existence. So this sort of stems from the fact that people originally thought the atom was indivisible. Then we decided it wasn't. We found protons and electrons and later neutrons. So people decided they were indivisible. And through some work in the mid-19th century, we decided that actually the nucleons, the protons and neutrons, appeared to have 3 mass centers inside them. It looked like they were not indivisible, but actually had 3 things making them up. And that meant that the relative charge of 1, which people used to think was the absolute unit of charge, could no longer be the case. And these mass centers inside the nucleons had fractional charges of the electron charge. And those mass centers are what we call quarks. And we believe they're indivisible. We also think the electron is indivisible. So the quarks and electron, and then the neutrinos that we'll add, are what we might describe as fundamental. They are indivisible. We might call physics a reductive subject. We're looking to break it down to the building blocks. And not all areas of science lend themselves to that. Certainly the social sciences, it often is totally inappropriate. But for physics, it has yielded amazing results. And we do build back up, but by getting to the simplest, we can build our theories from the ground upwards, and that's been a very powerful approach. And the standard model lays out our current understanding of those physical building blocks, the particles themselves. So this is what we now believe is the case. So in the column I'm labeling hadrons, that's where the quarks sit. So the up and the down quark would be described as the first generation quarks. The charm and the strange, the second generation quarks, And the columns have meaning. So strange quarks have properties similar to down quarks. Charm quarks have properties similar to up quarks. If a strange quark decays, it's a good bet that it will decay into a down quark. Now, strange quarks are heavier than down quarks. Top quarks are much heavier than charm or up quarks. So as we go down the generations, we get heavier. The down and the strange, as you could see from your formula sheet, both have a charge of -1/3. Now, in the lepton column, we've got that familiar thing, the electron. Now, we might just have touched by now on the electron neutrino, the fact that your GCSE understanding of beta decay was slightly incomplete. But it turns out the electron has a big older brother called the muon. It has the same charge, -1, but it's much, much heavier. Okay. Now the symmetry here is amazing. So the hadrons and the leptons are very different things. Protons are made up of up and down quarks. Electrons go round on their own. But this idea that we've got 3 generations and each generation has a pair of particles is really very neat and quite amazing. Now the syllabus wants to show you some of this beauty and symmetry, but we would need the entire 2 years to teach you even the basics of the standard model. And therefore we reduce the complexity by removing some particles that allow us to still show you how the world changes by accepting the existence of higher generations, but removing enough of the complexity to make it a manageable subject. So if you look at your formula sheet, it only tells you about 3 quarks, the up, the down, and the strange. The other 3 are there, but you will never be examined on them. With the leptons, we can't be quite as simple as that because there's something very much intertwined between an electron and an electron neutrino, a muon neutrino and a muon. They're very different because a muon is large mass, charge of -1. Muon neutrino is very, very low mass and neutral, but they are in some sense intertwined. So if we want to show you the muon, we can't do so in any sensible sense without also showing you the muon neutrino. The next part of the standard model is that every particle has an antiparticle. So this is what is termed antimatter in everyday sort of notation words. The standard model says that if there is an up quark, there must be an anti-up. If there's a down quark, there must be an anti-down. And apart from mass, all of the properties will be opposite. So where the up quark has charge +2/3, the anti-up must have charge -2/3. And that's true for all of them. The down, -1/3, charge becomes +1/3. Now you'll notice that I've added a new property here, baryon number. Now I'd prefer this to be called baryonness because it's a property like charge, but it's assigned a number, often called a quantum number. And all the quarks have +1/3, which means all the antiquarks have -1/3. But we're not limiting our antiparticles just to the fundamentals. The composite particles, like a proton, as we'll see in a few minutes, made up from ups and downs, has an antiproton equivalent. The neutron has an antineutron. The mass of the proton and the antiproton will be identical, but the antiproton will have a charge -1. It'll have a baryon number, -1. Occasionally, antiparticles get special names. So the anti-electron is usually called the positron, and the electron also is called the beta particle. Well, now we need to call the electron a beta minus because a positron is going to be a beta plus. Okay, the beta particles being high-speed versions of the electron emitted from a nucleus. Now, just a quick check. So pause the video and have a look at these questions. It's obviously a made-up particle, but for the first two, have a look and check that you're happy, and then press play again. So welcome back. Hopefully you realize that if the charge on the Hawk particle is +2, the charge on the anti-Hawk must be -2, whereas the mass will remain the same. So the anti-Hawk will have a mass of 2 grams. We don't have a concept of negative mass. From your formula sheet, you'll have found that the charge on the neutrino is 0, the up quark is +2/3, the strange quark is -1/3, and the positron is +1. So, starting to look more deeply at our standard model by looking at the leptons. Leptons go around on their own, so they are fundamental particles. And you'll remember that the 4 we talked about in my table that are on the syllabus are the electron, the muon, and their associated neutrinos. Okay. Some students occasionally get muddled up and think an electron neutrino is like an electron. It isn't. It's just that when we create an electron or a muon, there is usually some form of neutrino created as well of the same type. So the other type of particle, the other column that I had in my standard model was the hadrons. So the hadrons are all made of quarks, but quarks never go round on their own. So scientists have tried, and we have never managed to isolate an individual quark. So when you hear about the LHC at CERN, the Large Hadron Collider, well, it's something that collides large hadrons, large things made up of quarks. Okay, and there are 2 ways that quarks can come together as particles. They either join in 3s, 3 real quarks or 3 antiquarks. So the baryons, but we might also talk about the antibaryons, Q bar, Q bar, Q bar. I wonder if I've neglected to mention that the way we show in notation that something is an antiparticle is we put a bar on the top. So the Q here stands for any old quark, and Q with a bar on the top stands for any old antiquark. Mesons are formed by a quark-antiquark pair. So we could have up, anti-down would be a meson. Now, it's understandable that these names are off-putting. They are hard to remember, but you've got to get there. So my analogy is learning of a language, particularly if you learn in a school setting. Grammar takes a huge part of the time of teaching a language, and you can be really hot on your tensors and your subjunctive voice, but if you don't know the vocab, you're lost when you end up trying to use that language. And it's just the same here in particle physics. You have got to be clear very quickly in this subject. When somebody talks about a baryon, they mean a group of 3 quarks. And if you're not, you'll be playing catch up all the time, trying to decide what it is we're talking about. So these are something you need to either write some flashcards and keep looking at till you're sure, or test your friends, or write them and stick them on the back of the toilet door, whatever it takes. But you've got to know these things. Now, you'll see in the formula sheet, which I've taken a snapshot of here, that another property of quarks is their strangeness, and we've not talked about that yet. It's this problem of we've got to pick an order in which to teach it, and I believe that we can leave strangeness. However, just to mention here that there's 2 types of meson the syllabus is interested in. The pi mesons, or pions, have a strangeness of 0, which suggests they're made of ups and anti-ups, downs and anti-downs. The kaons have a strangeness plus or minus 1, which means they must have a strange or an anti-strange particle in. And a word of warning, a place I've seen students get mixed up in the past, you'll remember one of the leptons is called a muon. Now, it would seem likely that a pion, a kaon and a muon are somehow similar, but they're just not. Pions and kaons are similar, they're both mesons. Muons, on the other hand, are leptons, and very different indeed. Then the standard model asks, how do we build up the particles we see in everyday life? For example, the proton turns out to be the particle that's made up of quarks up, up, down. It's a baryon made up of 3 real quarks. So we, for the charge, simply take the charge on each of the individuals, 2/3, 2/3, minus 1/3, add them up, and we get +1, and that is indeed the charge on the proton. You'll note that for the antiproton, finding its antiparticle in quark terms is simple. We just put a bar on top of each of the quarks. We make each one of them the anti. Now, there's another particle here, the up, down, down, that I want you to work through and work out what the values are, along with the antiproton, although from our earlier rules, you should be able to just state the charge and the baryon number of the antiproton. And then there's this other particle here, up, down, strange. Now, you don't need to be able to name that particle in the syllabus, but you still need to be able to apply the rules. Okay. So please pause the video here and try and work out the missing values in the table for yourself. I really recommend that you do that rather than simply just waiting for the video to run on and tell you. It's good to practice these things. So welcome back. Here, hopefully you got the values right. Don't worry about this errant antibaryon floating up here. I'm not sure what's happened about that in the near the top left of the table, but hopefully you can check all your values. You'll see that the charge for an antiproton is just the opposite. It's just -1. This up-down strange particle has 0 charge. It's in some sense a bit like a neutron, but it's going to be heavier and it's going to have some strangeness. Similarly, we can do the same for the mesons. So again, please pause the video and work out the missing values using the ones here. So anti-up, well, up is 2/3, so anti-up must be -2/3, and down is -1/3. So this has a charge of -1. Now, it also has a baryon number of 0, because mesons are not baryons. They're in the hadron group, but they're not baryons. They have 0 baryonness. Now, I mentioned earlier about strangeness, and we're going to skirt around strangeness for now. Nevertheless, I just want to point out that the top 2 mesons are pi mesons because they've got 0 strangeness, and the bottom 2 are k mesons because they've got some strangeness. We then use a superscript above the label pi or k, and that denotes the charge of our meson. So we worked out that this was -1, so that -1 is used in the name, and note that I've just learnt a new feature on this record item where we show the minus like that. So you can already tell from this plus here that you're going to end up with a charge of +1, but still pause the video and check that out for yourself. I know all these names are difficult. It will just take practice. Hopefully you got all those for yourself. You know that we can have a K0, and we can also have pi0, a pi meson which is neutral. You'll notice that they all have a baryon number of 0. So this is a good point for a quick checkpoint. So can you explain to yourself what's a quark? So the answer might be it's a fundamental particle that is used to build up baryons and mesons. Okay, so have a think about each of these and try and check your notes to see, have I written something down about these? If not, should I go and look in the syllabus? Should I go and look at Caboodle? Now, my advice would be, don't go and look at Wikipedia. If you're going to use Google, please type in A level and try and focus your searches on things that are relevant to the A level, because we can make whole PhDs out of a single one of these words. So if you go onto the internet, you may well get material that is way above what's required. Okay, then have a go at trying these two, and we can go through those in class. So that's it for today. I hope you've enjoyed it. The idea of these videos is that you can rewind, listen again, check your notes when you get to a point with some questions and you're not sure, you can go back. So because the language is difficult, rather than only getting one hit in class, the idea of these videos is not that you watch them once through, but you've got them there as a reference. Thank you very much.